Okay, so let's finish the problem that we started last time. So let me quickly summarize what we were doing. We had a semi-infinite plate or a half space. So this extends in in both directions infinitely. And we are imposing a point force in the normal and tangential directions at a point. So x1 points downwards, x2 is that way, theta is in the usual direction. And these are loads per unit thickness. So what we should think about is sort of, let's say, a plane strain scenario. Our solution also holds for plane stress, but it's a line load. So the load per unit thickness is n. And I assumed without loss of generality that the thickness here is equal to 1. In that case, you can think of n as being the load that's implied, that's imposed. Okay, so then we sought what the area stress function was. So we proposed a problem-tailored form, and we first said, well, okay, let's say that there's a separation of variables approach that such an approach is applicable. And then we argued that for equilibrium to be meaningful, the R dependence must be linear, and then there's another function, eta of theta. So that function is general, so we didn't know what it was from the outset. So then we went ahead and imposed compatibility, and once we imposed compatibility, we found out a general form for eta where these were initially constants. So to find what the constants were, we imposed boundary conditions. So there are two sets of boundary condition, point-wise, sigma r theta and sigma theta theta. It's 0 on the top surface, it's traction-free. But as soon as we invoked the separation of variables approach together with linear dependence on r, those were identically satisfied. So what we imposed was the integral boundary condition. In other words, the stress distribution must balance the normal and tangential forces. And with those, we found out what these two constants were, and thereby what the stress distribution is. There is only sigma rr, and it has that form. Okay, so that's where we were. Now, what I will do is I will proceed with the discussion of displacement. So it is an intricate problem, so it turns out you need sort of all your portfolio of tools for solving ordinary differential equations to solve for the displacement field. What I will do is I will try to go through it sort of in as much detail as needed for you to be able to pursue the solution to full results. But I'm going to skip some details. Not too much, actually, but I'm going to skip some details that you can fill out eventually yourselves. So we have everything on board. So let me proceed with the displacement. So again, we are in a cylindrical coordinate system. I have to remind you what the appropriate relations are. Recall that the body force is negligible, so the equations that I'm about to write are special for that case. So as usual, the first two terms of the displacements, they have to do with the area stress function. And then there is a second contribution that fixes the shortcomings of the displacement if I had not written that additional term. So the additional term is that and this one. So and psi is a function that we have to, of course, as usual, find out. And it's subject to the usual requirements. So Laplacian of psi must be equal to 0. And eventually, there's a second condition, remember. And in cylindrical coordinates, it takes this form. What I will also remind you is just going to, when you look at your notes, it's going to make your life a tiny bit easier. Laplacian of phi, I told you last time, that is equal to sum of the diagonal stresses, and sigma theta theta is identically 0. So Laplacian of phi is equal to sigma rr. I don't have to reevaluate it. I already have written it on the board. Okay, so now we want to find out what psi is before we can evaluate the displacements, and that's going to take a short while. So as usual, we start with the second condition, and we find out a form that we later on restrict by imposing the first condition. That's what we have always done. So let's proceed with the same procedure. First, I write down what the requirement on C is, the second one. And that's equal to sigma RR. So minus 2 over pi r and cosine theta plus v sine theta. Okay, so I'm going to integrate through r and then divide by r. Okay, so I will have minus 2 pi ln r, and then I'm dividing by r over r, and cosine theta plus v sine theta. So the derivative was with respect to r. I could have here an arbitrary function of f. So just for convenience, let me not call it f. We've done this before. I'm going to call it f prime of theta. So this function is derivative of some other function. And I divide by r. And so that's the result. So that's r. That's del c over del theta. Okay. So then we integrate once more. And we find out the general form for c. So minus 2 over pi ln r over r and sine theta minus v cosine theta plus 1 over r f of theta. Okay. Now, the derivative was with respect to theta. So here I can have an arbitrary function with respect to r. So I'm going to express that function just again for convenience as the integral of some other function g. Okay. Is there a question? Question? Go ahead. Sine? Right, I'm integrating, right? Okay. It's too early. Okay. All right. So that's the general form. Again, here I put the prime just for convenience. I already made use of it. Here I introduced an integral, the function through an integral, and I'm going to make use of that convenience later on. Okay, so those are the functions that we need to, well, the functions f and g are now what we need to find out. And so that's now a general form, and I can impose the first condition to find out what f and g are. So let me do that over here. So 0 has to be equal to the Laplacian of c, and we have already indicated last time what the Laplacian in a cylindrical coordinate system is. I'm just writing that once again. Okay, so this is one part where I'm going to skip a few lines. You just have to go ahead, plug in C, evaluate all of these terms, collect everything together. Okay, so when you collect everything together, you will see that an r cubed term appears here and there. So I'm going to modify it slightly, divide through r cubed, etc., rearrange. But eventually, just after a few lines, you will reach the result that this condition is equivalent to the following. Really, I'm not skipping more than just 3 or 4 lines. And now you will probably see why I introduced the function g through an integral, because here there's an integral with respect to r. So when I take that integral, instead of having to deal with second derivatives of a function, I only have one derivative. And when I take a derivative with respect to theta, that term disappears anyway. So everything looks fine so far. So what we have to now realize is that there are two terms. The first set of terms here, they are a function of theta alone, because f is a function of theta alone as well. And g is a function of r alone. So let us call this one a term beta, and this one has to be minus beta. This is term number 2. And let me call this term number 1. And I'd like to work out the details of the solution, again, sort of in an outline form. So first of all, let me tell you what the solutions are. So g of r is equal to alpha over r. Alpha is some other constant. Beta is also a constant. I don't know yet what it is. So that's the form of g. And we also have f. And f has beta in it, plus some other terms. And those terms include 2 free additional constants. Okay, so the constants overall, if you look, there seem to be 5 free constants here. Alpha, beta, e. Well, sorry, 4 free constants. Right? Alpha, beta, e, and f. Okay, so that's the solution, right? And here, for your reference, I'm sure you could do this on your own by referring to your ordinary or differential equation course. But I'd like to outline here how one obtains these two solutions, just so that eventually, for your reference, you can complete it in full detail in the future. So let's start with 2. Okay, so the differential equation we're trying to solve for is r cubed g prime plus r squared g is equal to minus beta. That's the first equation that I'm trying to solve for. It is a non-homogeneous differential equation. It will have 2 parts, right? So let's outline what those parts are. Let's begin with the homogeneous one. So the homogeneous one has to satisfy r cubed gh plus r squared gh equals 0. And that's a separable differential equation. And so separable, therefore, delivers you that gh is equal to alpha over r. Okay, so here is where I'm skipping the details. I'll just indicate what it is, and then the solution comes immediately. You can also see what the solution is by inspection, I suppose. So that's the homogeneous part. And then there is the particular solution. Now, the particular solution, again, you may wish to find by inspection, and for sure you can. But otherwise, what you can do is you can use a method which is called the method of variation of parameters. So all of these methods have a certain classification according to the complexity of the ordinary differential equation you're trying to solve for. So you look at the ordinary differential equation. You look at whether the okay, so we assume it's linear. So then you look whether the coefficients are constants or not. If it's constant, you do one thing. If not, you do something else. And then usually one difficulty is the particular solution. And this method works when you know what the homogeneous solution is, and it's hard to find what the particular solution is. In this case, it's not too hard, but just to remind you, because it falls within this classification, what you do is, okay, I don't really know what the particular solution is. Perhaps it's something complicated I cannot guess. I'm going to say that it is some function w times g of h. The constant in g of h is irrelevant, so let us omit the constant and just say that it's equal to w over r. Okay. So I omitted the constant in gh. Okay, that's the solution you start with. And now gp has to satisfy star, the differential equation. Okay? And through that requirement, you find out what w is. It's almost like the method of reduction of order, but you're not reducing the order, you're just finding what the unknown function w is. So in this way, you find out what w is, and w is equal to beta over r, which you could have guessed, and therefore g of p is equal to beta over r squared. So on the other board, I had written already what the solutions are, and now we know what one solution is. G is equal to alpha over r plus beta over r squared. Okay? So this one is done with. Do you have any questions here? Okay. So eventually, if you want to fill out the details, you just need to look at the particular methods, and that should guide you. And now the second method, right? I have the forms of the displacements here. I don't want to really erase this. Actually, I need pretty much everything here. So let's see, what shall I do? Okay, the solution, right? So you have this in your notes. Let me erase this board. And I'll just leave this much for F. Let's move to 1. And let me also outline what the solution there is. So this is our second differential equation. So f double prime plus f is, so that equality that I had indicated under equation 1, it's equal to this plus beta. Okay, again, it's decomposed into homogeneous and particular parts. The homogeneous part, it's simple. So f prime of h plus f of h is equal to 0 is the simplest thing you can hope for. Eventually, the solution is, of course, sine and cosine. Let me indicate the constants as e multiplying sine and f multiplying cosine. Those constants, of course, are free constants. Okay? So then the particular solution. So in this case, when we seek the particular solution, we are going to use the method of undetermined coefficients. So when you look at the classification, there isn't always only one method. There can be more than one method that applies to a certain case. So in this case, what you would say is that the particular solution is something that has to do with some constant, perhaps, times what appears on the right-hand side. Okay? The problem is that what appears on the right-hand side as the non-homogeneous term, it's a term that appears in the homogeneous solution. So you cannot put the same thing proposed as a particular solution because that would just be meaningless. So the idea is, in that method is, well, so first of all, Fp has for sure beta in it, right? That identically satisfies double star. And then you say, well, sine theta is already in the homogeneous solution, so what I have to do is I have to throw in this particular case, theta as a coefficient. Okay, so then what you would propose is you throw in a constant, theta sine theta, plus another constant, theta cosine theta. So these thetas come from the fact that right-hand side appears in the homogeneous solution. Okay, so that's the form of Fp that we propose. And now this solution has to satisfy double star. Okay. And that is the method of undetermined coefficients. So G and H are as of yet coefficients that I need to determine. So I plug in this form into the differential equation. And I find out that G is equal to 2v over pi. And H is equal to 2n over pi. And therefore, F particular is beta plus 2v over pi theta sine theta plus 2n over pi theta cosine theta. Okay. And so now when you look at the solution that I had indicated at the beginning, you see that it is, right, a term from the particular solution, homogeneous solution, the remaining part of the particular solution is there. Okay, it's not that hard after all, but I just saved you some time by skipping through the details. Okay, so now we are essentially done in determining what psi is, right? So I have a function g that's fully determined. I have a function f that's fully determined. So let me now pull up this board. This is what we were doing, right? I have a form for the displacements. I know what the air stress function is, and I need to determine what psi is, and psi has that form, okay? F and g are now determined. So I know what psi is. So now I'm going to go ahead and plug in air stress function phi and psi and evaluate what the displacements are. Okay. So again, I'm raising this board, sort of like my working board here. So 2 mu ur. So the form of phi is also down here. So del phi over del r with a minus sign. So it's going to be minus eta. Okay. And then the remaining term has to do with plus omega r del psi over del theta. So I'll just write down what the result is. It's not too hard. So the first two terms survive. The last term drops. Minus 2 over pi ln r over r and cosine theta plus v sine theta plus 1 over r f prime theta. Okay. And I know what f is, so I can evaluate f prime. And the second one is 2 mu u theta. So it's minus 1 over r del phi del theta, so that is minus eta prime in this case, plus omega r squared, a derivative with respect to r. And if you look again, look in your notes, or if you see the board. So I need to take that derivative, that's fine. This one over here, it's easy, and here g automatically comes into play. So I'm just going to write down the result here. So that's the form. Now, you have to plug in F and G in here, and you have to collect terms, okay? That part I'm also skipping, okay? Some straightforward calculations. Let me first note here, eventually, if you do that, what type of constants appear as free constants. So first of all, there is A and C that will come from phi, so 2. And then there was a E, F, alpha, beta, okay? So in this form, if you plug in everything, there are undetermined coefficients, which are, or let's say constants. Alpha, beta, A, C, E, F. Okay, so a total of 6. Now, among these, beta, it turns out, if you plug in everything, beta never appears in UR. And if you plug in, it appears in F and G, they cancel out. Okay, so this term actually does not appear. Okay, it's not 0. It's just that it doesn't appear in the displacement. So really, it's irrelevant to us. So there remain 5 constants, right? But among those 5 constants, you can combine 2 pairs into a single constant. And we've done something similar before. I don't really care what the individual values of C and E are. What I only care about is their sum in this equality. Okay? And likewise, I don't care what exactly A and F are. I only care about this quantity. Okay? Okay, so if you plug in F and G, and if you define these constants, and if you group everything nicely, you're going to end up with the particular forms of UR and U theta. And now those results I'm going to write down over here on our problem summary. So the final expressions for displacements. So I will group them in 2 ways. One, there is a sine theta term, always, and a cosine theta term. It appears in our solution, so I'm going to group those separately. And then sometimes there is a factor theta appearing. And also terms multiply either the normal force or the tangential force. So okay, let me first write, and then I will double check to make sure that I've written correctly. So that's the sine term, and then the cosine term. Let me write U theta with a different color so that it stands out a little bit, at least. All right, so now if we put everything in this form, it's rather neat actually, and we see that there are precisely 3 constants remaining that need to be determined, d1, d2, and alpha. And as usual, these constants have to do with rigid body motion. Okay? There is translation that we need to restrict, and there is a rotation that we need to restrict. So precisely the coordinates, or the indices, indicate the rigid body displacement that this constant has to do with. So in particular, here, di is associated with rigid body translation along xi, and the constant alpha has to do with rigid body rotation. Okay. So if d1 is positive, the displacement, the body will shift right. d2 positive, it shifts up. If alpha is positive, it's clockwise rotation. It will rotate in the counterclockwise direction. So now we need to find out what these constants are. And what I will do is actually eventually first of all, the stress field, it doesn't matter, right? But for the numerical solution, it turns out it also doesn't matter. So for instance, what I could do for comparison with the numerical solution, I could simply pick all of them to be 0. Okay, that is one choice. But what I'd like to do is I'd like to pick something that we have done before and pick something meaningful. So that as well, I am going to shortly summarize, let's say over here. And then we are essentially done. So to determine the constants, what we are going to do is we are going to choose a point. Okay, so this is our coordinate origin, and I'm going to move along the x1 direction through a distance L. And I'm going to pick a point. So this is the point r theta equals L0. Okay? So I pick theta equals 0 almost arbitrarily, and I pick this length arbitrarily. Okay? And what I'm going to say is that this point doesn't move anywhere. So in other words, when I go to the displacement field and plug in r theta equals L0, ur and u theta must be equal to 0. That gives me conditions eventually for which d1 and d2 need to satisfy. And additionally, what I will say is, and we've done something similar before when we were dealing with the cantilevered beam problem, I'm going to look at the rotation of that line, and I'm going to say that it is equal to 0. Okay? So those are the requirements that I'm going to impose. So let me just indicate what they are. So first of all, displacement ur at r theta is equal to L0. 2 mu ur, if I want that to be 0, and if you plug in r theta equals L0, you will end up with, among all of that complexity, because sine theta is equal to 0. If there's a theta term, it disappears, etc. So you end up with something very simple. Plus d1. Okay? And from this, you find out that d1 is equal to minus 2 omega over pi 1 minus ln L. And, okay. So this, let me highlight, I'm not doing something that is physical. This displacement boundary condition is not something that is appearing anywhere in the problem. The issue is I want to get a unique displacement field, and the stress field I have found out holds whether this body is here or there or there, or it rotates by a certain amount. That is what I'm trying to fix. So I want to say it's not anywhere, it's here. And it cannot rotate arbitrarily about this point. If it does, stress field doesn't change. I want to restrict that as well. So I'm trying to fix my displacement field in this case. Again, that's how it differs from earlier solutions where we had some well-defined displacement boundary condition. So I immediately find out what D1 is. And similarly, you say that 2 mu u theta is equal to 0. And from this one, what you will find out, again, by here, let me skip the details. D2 is equal to 1 over pi 1 minus 2 omega v minus alpha omega L. Okay? So I need to find out what alpha is, and that's the last part. Again, we've done this before. Let's recall rotation. And in this case, in cylindrical coordinates. So the rotation matrix component is omega theta r that we want to look at. And omega theta r, as it was in the Cartesian coordinate system. For instance, there we used to look at omega 2,1. It would be 1/2 h21. H is the displacement gradient minus h12. So in this case, it's theta r minus r theta. And this is greater than 0 means it is counterclockwise rotation. Okay. I'm just going to record here for your reference again what the displacement gradients are. So h r theta is equal to 1 over r del u r del theta minus u theta. And h theta r is equal to del u theta over del r. So at that point, therefore, we restrict u r, u theta, and omega theta r. That's what we are doing, right? So, and from the last requirement that omega theta r has to vanish at r equals L, theta equals 0, you find out that alpha is equal to, actually, it's the calculations take a few lines, but the result is very simple. It's 2v over pi L. Okay, so that's about the solution. There's nothing more to do. So now I'd like to do a numerical comparison between analytical and, well, it's comparison between analytical and numerical solutions. And there we have to do one more thing, which I can immediately squeeze in, if you like, or maybe just remind you, right? So the calculation will eventually work in Cartesian coordinates. All my results are in a cylindrical coordinate system. So I need to convert from one to the other. So for that purpose, the transformation for vectors we've already done in the very first lecture on mathematical preliminaries. You can refer there. And eventually, I have to convert the stresses as well. And for that, I will use the Morse circle. Okay? So that's how I can eventually compare numerical and analytical solutions. So let's proceed with the comparison. And I have my solution here in case we want to refer to it. And OK, so let's proceed with the comparison of the numerical and analytical solutions. So in this case, it turns out that the challenging part is not really the analytical solution. The numerical solution, to get a good numerical solution with this type of problem is really not easy at all. The problem is that we have a singularity. And if you look at our solution, the singularity is present not only in the stress field, but eventually there is a logarithm term in the displacement field as well. So the stress is singular, displacement, eventually it's also singular. So, and if you want to get a good stress field, you have to have a very good mesh. So what I've done here, first of all, you can look at the two pictures. My coordinates is x1 and x2. So to align that with the picture in the numerical setting, so this is x1, that's x2. So our picture is now rotated, right? So the normal force I'm talking about is in that direction, that's n, and v would be in this setting, in this direction. And this is the point at which I am going to apply apply the forces, okay? Normal force, tangential force. So this is the traction-free surface. Here, I don't impose any boundary condition, right? It's traction-free, all right? So this portion, I just picked a domain there that something I draw with a curvy line. I just picked a square, right? Now, here, however, I don't know what really the boundary conditions are. In fact, in this problem, there is no boundary condition there. It's an infinite domain, so it's not clear what I should be doing. So it turns out that actually it doesn't matter what you do if you want to get a good stress field. So for instance, what you can do is you can simply fix this portion. It will be an end effect as long as the domain is large enough with respect to the variation of the stress fields. I will show you that. Okay? So eventually, if the domain is deep enough and wide enough, so it represents almost like a semi-infinite domain, the stress field will look perfect. The issue is if you want to match the displacements, that's the tricky part, because there is no boundary condition on displacement. Okay? So to have a solution that matches eventually the displacements as well, numerical versus analytical, so you can do a comparison and check if my analytical solution is correct, for instance. And also to ensure that the stress field distribution, analytical versus numerical, is excellent even when the domain is not large enough. Okay? So what I will do is something that is clever thing to do in these types of problems. Here, which represents a cut from the infinite domain, I'm going to impose displacement boundary conditions. Okay? I'm going to say what the displacement is. You always need boundary conditions. And the displacement is going to come from the analytical solution. Okay? So I'm going to take the analytical displacement field and impose it here. R changes, theta changes. I'm going to tell it exactly what it should be. And then, of course, you expect actually an excellent perspective of almost the size of the domain. Okay? But if you don't do that, it's almost impossible to match the displacement. So that's the setting. And what I've also done is I have refined the mesh, as you can see. Picked a criteria that refines the mesh towards the point of application of the force so that the solution is efficient, right? Why? Because we expect strong variations in the stress with 1 over r in the vicinity of the point of application of the force. But far away, you don't need that much quality in the mesh. Perhaps the mesh is already fine enough there, all right? So that's what I'm doing. It's not a finite element course, but by this time you are familiar with these concepts. And perhaps you have already taken an elective course on finite elements. OK, so that's the setup. So that being the case, so presently I have a set of parameters that I have defined. The length of the domain is 1 by 1. And the force is fairly large with respect to this domain size, actually. And let me show you what the solution looks like. Okay, so now I'm going to show you a couple of pictures. Here, for instance, so x direction, y direction, normal force, vertical force, and tangential force, sorry. And this is the sigma RR distribution, radial stress distribution. Okay, the radial stress distribution, right? So you see there's a r and theta dependence, and it looks fairly complex. Now, the domain, it turns out, with respect to the loads and therefore the variations of the stresses, it's not large enough. So you don't see the whole picture here yet. Okay? The domain has to be larger for the whole variation to be more clear. But let me proceed at this stage and look at the tangential stresses. So it may be hard for us to believe, OK, we found out that theta, theta, and r theta are 0. But are they 0? They are really 0, almost everywhere. Okay, so I'm saying almost everywhere. Where it's not 0, it's a negligible part that is the defect of the numerical solution. So with respect to this picture where the variations are significant, TT is 0 everywhere, okay? All the way to the tip of the point of application of the force. RT, it's not an exciting picture, it's also 0. Now let me highlight the x, 1, 1, 2, 2, and 1, 2 shear components of the stress in Cartesian coordinate system. It's not 0, none of them are 0. Okay, so 1, 1, 2, 2, 1, 2. Okay? Nothing is 0. And they are fairly complex. So in some sense, that's a nice thing about working, in this case, the cylindrical coordinate system. It sort of lumps all of this into a single thing where you see it's non-zero, everything else is 0. Okay? I'll do one more thing. What I'm going to do is I will, in this case, for instance, I will take a cut at a certain angle. Okay? And I will take a radial cut at, in this case, at theta equals pi over 4. And I will compare the variation of the radial stress, that's the only non-zero component, numerical versus analytical. Okay? And it's this picture. Okay? It's perfect match. There are two lines. They're right on top of each other. Okay? So the match, the domain is very small. The match is perfect because I've pick the, let's say, boundary conditions by imposing exact analytical displacement boundary conditions. And that was a judicious choice, and that allows, I'll say, excellent match. So here I'm checking two things. Is my numerical solution good enough? And also, is my analytical solution correct? Because if it was not, there would be no match, right? I'm doing two things at once. So the match is great. Again, you can look at sigma TT and RT. There are some numerical wiggles, numerical dust that's really negligible. It's for all practical purposes 0. So I'm not going to show you those again. Okay? So now this is the exaggerated displacement field. Okay? I multiplied the displacements by a factor of 20. And of course, displacement at the tip is singular. So numerically, you cannot capture singularity right at the point of application of the force. But it's super large. Okay? So when you multiply through additional factor of 20, it looks weird like this. But what I want to show you here is the condition I've imposed. This length, it's L. And our condition was at R equals L, theta equals 0 is this point. There is no movement, and there is no rotation. Okay? So the thin black line here, perhaps it's hard to see on screen, but there's a thin black line that indicates the original position of the original shape of the square that I'm analyzing. Okay? So the body has not moved anywhere, and it is perfectly tangent to that line, so it hasn't rotated. That is the condition that we have just imposed. Okay? But really, it's not important for a comparison between numerical and analytical. This is just to demonstrate the choice that we have made. Okay? Again, I'm not going to show you this again. We can compare displacements. This is the radial displacement. Okay? And again, I'm doing two things, right? Numerical solution is good, it's correct, and it matches the analytical one. So analytical solution is, we've gone through a lot of detail, but it's correct. Okay? This is the tangential one. Okay, these are non-trivial variations, right? I mean, function-wise, there is only theta, sine, cosine, and r, or logarithm r appearing. Okay? But eventually, that's sufficient to give you fairly complex variations. Right? So that's the solution. Matches quite good. Now, what I like to show you is the effect of domain size. Okay? The effect of domain size, before, what we always did was we had some approximation. Let's say the solution is expected to be good if plane stress condition is satisfied, etc. Right? We had to increase or decrease some parameter, like geometrical parameter. We had to make the domain longer or thinner, whatever. So in this case, there is no such restriction. Right? But I have the variation of the stresses. And I don't really see the whole picture here. The only thing I'd like to do in this case is presently see the full picture with the stresses. Okay, so just to show you that, I'm increasing the domain to 10 times the size along every direction. Okay, so now it was 1 by 1, so now it's 10 by 10. Okay, so now you see more clearly what these variations are, right? And I've discussed this before last time in the first part of our solution. So N like this, V is like this. In this case, N and V are both the same. And ahead of the point of application of the forces is always compressive. So this is the sigma RR field. Behind, depending on their relative magnitudes, it could be tensile or compressive. So that's what you see here. Here it's tensile. Here it becomes compressive. Theta is less than 0. Theta becomes positive. It's always compressive. And then there is this line here that is the meeting place between tensile and compressive. that is sigma RR 0. Okay? That you can sort of judge. It's roughly, in fact, not roughly, it's exactly minus pi over 4. Why? Because n is equal to v, pi over 4, 1 over square root 2, minus pi over 2, and then they cancel. Okay? So everything sort of verifies our picture of the solution. Again, you can look at the, let me just show you sigma RR. The R is in log scale because variations are very fast, but match is perfect. And then you can look at UR, UT, and everything. Now, one last step. I'd like to increase the domain size even further. So here's where it pays off to have a good mesh, because if you want a fine mesh always, everywhere, then it becomes very expensive already, even in 2D. Okay, so the stress solution, everything is going to still match very well. Now what you see here is it's almost like infinite with respect to the region where things happen, right? If you just omit that region, this is sigma RR, everything is 0. Stresses decay to 0. Okay? What I like to show you, right, is the displacement field. Okay? So displacement field, I always, of course, have a condition, okay, on UR and the rotation, but there is no condition on the displacement field. It's not a problem where I have some prescribed end effect or end condition. So this is what you have to be careful about when you want to do a comparison with a numerical solution. And again, that's why it pays off to have a clever boundary condition imposed on your numerical solution. But essentially what we've done here is that we've verified that through our efforts, we've obtained some solution that is, well, at times maybe a little bit painful, but perfect match with numerical solution. Okay. And again, I highlight actually the numerical part is a little bit more challenging in this case. Okay. So if you want to get a good numerical solution, you have to work on it. Okay. Questions? All right then. Thank you. And next time we move to our last problem.